very happy to welcome Javier Esparza from the Technical University of Munich to give the invited talk on population protocols. So Javier, of course, does not need an introduction to a theoretical computer science audience, but I will say a very few things. So he's professor of theoretical computer science in Munich, and he has been working on and has a lot of very fundamental results in the fields of automata theory, infinite state verification, parameterized verification, and more recently, models of distributed computing. He also has several fundamental results in the theory of Petri nets. But without giving a long list of awards and honors and best paper prize awards that he has, I will ask Javier to take it away. Just one request before I start. If you're not the speaker, please mute yourself and unmute yourself when you want to ask a question. I will also be monitoring the chat. So if you have a question, urgent question in the middle, just put something in the chat and then I can call upon you. Okay, so Javier, please go ahead. We are really happy to have you here at FSTTCS.
Okay, thank you. Thank you for the introduction and thank you very much for the invitation. So this is a talk on population protocols. And it is a model of computation that is becoming increasingly popular, fitting the name, right? But I don't think I can assume that you all know it. So I'm going to introduce it. And maybe some of you know that I like to introduce it by telling stories about ninjas, right? So today is not going to be an exception. There will also be some stories about ninjas. My apologies to those of you who may already have seen some of these stories. But in fact, today they will be a bit different than the ones you may have seen somewhere else. So, you know, the story is about the deaf black ninjas in the dark. And the idea is that the deaf black ninjas are a secret society of warriors. And it's so secret that they don't know each other. And they don't even know how many they are. But the deaf black ninjas, they have got a message from the leader of the society telling them that they should meet at a certain garden in the dark at midnight to attack a castle. Okay. The problem is that, well, they will only attack if at least 100 ninjas show up, and with COVID and so actually nobody knows how many ninjas are going to be there. So the problem is when the ninjas arrive in the garden, this is what they see. It's dark, they don't see anything. And they also don't hear anything because they are all deaf, right? This is the deaf black ninjas society. So the problem is, how can they find out whether they are 100 or not? Think about it for a moment. I mean, the usual ideas of raising hands or counting, they do not work really, right? So ninjas, the idea is that the leader of the society has told them how to solve this problem, how to do this. So he has told the ninjas to carry a purse with one pebble, and when they arrive in the garden, start wandering randomly around the garden, right? And then proceed as follows. When two ninjas bump into each other randomly, one of them gives the other all its pebbles. Okay, and then immediately you can see that if there are at least 100 ninjas, then eventually, because of the random behavior, eventually some ninja will collect at least 100 pebbles. Okay, and that ninja then at that moment knows, oh yes, we are at least 100. Okay, so then the second instruction from the leader is, if you know already that there are at least 100 ninjas, then whenever you meet other ninjas, just spread the word. Okay. So we can see this a bit more precisely. We can define now this a bit more precisely. Let's look at the protocol not for 100 ninjas, but for 4 ninjas. So the ninjas here are in one of these states, 0, 1, 2, 3, or 4. And initially, all ninjas are in state 1 because they have 1 pebble, right? The state corresponds to the number of pebbles they have. And then there are transitions like this, right? When 2 ninjas meet, if their combined number of pebbles is less than 4, then one of the ninjas gives the other ninja all pebbles. So one ninja keeps n plus n pebbles, the other 0, right? And we can see now happening, for example, if these 2 ninjas bump into each other, then one will keep 2 pebbles, the other 0. If these two ninjas bump into each other, nothing changes. If these 2 ninjas now interact, again, 2, 0. And now, if these 2 ninjas interact, then here come the new transitions, which say if the total number of pebbles is at least 4, then these ninjas already know that they are at least 4, and therefore they both go into a state 4, right? And in particular, notice then that if m or n, one of the two, is at least 4, then because of this transition, they will both go into state 4. So what happens now is that these two ninjas go into state 4, and now they start spreading the word, okay? And at this moment, all ninjas know that they are at least 4, and they are all happy, and they can start the attack, okay? Actually, I can even simulate this. And now, you know, this is really the protocol for 100 ninjas. I could set the threshold here. And imagine that there are 170 ninjas, okay, in the garden in the dark. And initially they have just 1 pebble. When they get 0 pebbles, they are going to become gray, so that we can visualize this a little bit. And if one ninja gets 100 pebbles in its bag, in its purse, it's going to become blue. Okay, so let's see how this evolves. So as you can see, very quickly, because these things happen concurrently, okay, very quickly many ninjas lose their pebbles. And now we have already 1 ninja here which has collected 52 pebbles. Can you see the cursor, by the way? Yeah. Okay, good. And so there are, now the protocol goes through a slower phase because there are fewer and fewer ninjas, such that when they both interact, something happens, right? When you interact with a ninja with 0 pebbles, nothing happens. So now it goes a bit more slowly. They have the ninjas but now you see they already got 100. And the moment that one ninja gets 100 pebbles, then everything goes very fast again, because they can just spread the word, okay? So we can do it again if you want. So very quickly, some ninjas get quite a few pebbles. Then there is this slower phase. And then at some point, this with 99, the one with 99 is waiting for an interaction. Now it goes, and now the 100 spreads very quickly around. Okay. So this is an example of a population protocol, a model introduced in about 15 years ago by Angluan et al., right? A formal model to describe, initially it was a formal model to describe swarms of mobile agents that interact randomly. And what is the purpose? The purpose is to decide the property of the initial configuration. In this case, does the initial configuration contain at least 100 agents or not, right? This is one example. Another example, for example, could be that there are ninjas of 2 kinds. The ninjas are red and blue. And the question is, do we have more red ninjas or do we have more blue ninjas? And the ninjas have to decide this property by themselves, okay? Now, since the late 0Ts, right, population protocols, the interest of population protocols shifted a little bit, because it was observed that they were also a model of natural computation. And the idea is that this is the case when agents are molecules or even atoms. And then population protocols are in slightly different flavors. In this context, they are called chemical reaction networks. And the idea is that, you know, the chemical reactions that we are familiar with, they can be seen as interactions between agents. Here you have 1 molecule of methane and then 2 molecules of oxygen. That gives you a molecule of carbon dioxide and 2 molecules of water. So you can imagine this as a reaction where 3 agents interact. And here the state of an agent, the state of a molecule, would be the specific chemical species it is. So now this molecule is in a state oxygen, and it could move to a state water, for example. Good, and this has actually given population protocols a lot of thrust, and there has been, for example, this NSF expedition in computing, which has, where population protocols was one of the main models that were being studied on the theoretical part. Or, for example, there is a very simple population protocol for approximate majority that actually Luca Cardelli and colleagues, this is a slide from a talk by Luca Cardelli, implemented in DNA. So let me just tell you a little bit now, be a bit more formal. So what is then a population protocol? In order to specify a protocol, you give a set of states. And in our example, this would be the states. Then you specify, you attach to each state an opinion. The property holds or the property does not hold, okay? Then you have a subset of initial states. In our case, by the way, in our protocol, the state 4 is the one which thumbs up, and the property holds, the others are thumbs down, right? The initial states, in this case, in our protocol is just state 1. And then you have transitions in which ninjas interact in pairs, right? For example, if two ninjas interact with contents of the purses 2 and 1, then they go to 3, 0, and so on. These are just, I have given you here four transitions, but there are more in the protocol. So let me introduce the notion of configuration. The configuration just tells you for each state, how many ninjas do we have currently in that state, right? For example, 9 ninjas in a state 0, 1 ninja in a state 1, and so on. And the configuration is initial if the only states that are populated are the initial states. In our case, in our example, we only have one initial state. So for example, this is an initial configuration with 15 ninjas around. So now if you fix an initial configuration, for example, the one with 4 ninjas, right? Then we have a reachability graph starting at this configuration. For example, now, well, the only thing that can now happen is that 2 ninjas in a state 1 interact, and then they are going to move to a state 2 and 0. The order here doesn't matter, right? This is a multi-set. You have to imagine this as a multi-set. And then you can proceed further, and then you will see that this is the reachability graph, the set of reachable configurations from the initial configuration. Now notice that this reachability graph for each fixed initial configuration is always finite, because the number of agents never changes, and therefore, since you only have a finite number of states, you can only have finitely many configurations. Now, in population protocols, you make the assumption that at each step, you pick a pair of agents uniformly at random and let them interact, okay? Then this gives you a probabilistic semantics for the model. In fact, in this way, we can transform the reachability graph for each initial configuration into a Markov chain. Consider, for example, this configuration. Now, the only way for this configuration to change is that you pick the 2 ninjas with 3 and 1 pebbles in their purses. Okay, any other pair is not going to change the configuration. Now, how many pairs there are? There are 6 pairs because we have 4 agents. So therefore, the probability of picking one pair is 1/6. So this transition gets probability 1/6, and the rest of the probability goes there. Okay, good. So then, as usual, we can define in Markov chains, we can define runs. Here, infinite runs. For example, one where you go here, and then, well, we don't know, I haven't drawn how many times we go around this transition here, but eventually we leave, and then we go over there, right? Okay, and then now with this, notice for each initial configuration, then we have as semantics a finite state Markov chain. Now we can formally define what it means that the protocol defines a property. Okay, and a property actually we are going to formalize as a predicate from the initial configurations into 0 and 1. Okay, or actually I should have written into thumbs up and thumbs down. Okay, and we say that the protocol decides a predicate. For example, it could be the predicate, you know, x bigger than or equal to 100, where x is the number of ninjas in the initial configuration, right? And we say that's the case if for every initial configuration, the runs starting at that configuration reach a stable consensus, the stable consensus given by the predicate with probability 1. What do I mean by a stable consensus? What I mean is that, for example, imagine that the predicate says that for an initial configuration, the result should be thumbs up, okay? Then the idea, or should be 1. Then the idea is that all ninjas must eventually agree to, it must be in states with thumbs up, and must stay in such states forever, okay? They have to agree on that and keep agreeing on that forever. So for example, here you have a protocol in which for this initial configuration, the output of the protocol, so to speak, is 0, okay? Because eventually all runs with probability 1 are going to land here or there, and we assume that there you only have configurations in which the ninjas agree to 0. Okay, and for this initial configuration, then the protocol yields 1. For this configuration, the protocol yields 2. Yields 0 again. Sorry. Okay. Good. So now we have the model, and our protocol, in particular, our example, decides the predicate x bigger than or equal to 4. Good. So we are interested here in succinct protocols, in protocols with a small number of states. Consider the protocol that we have just defined, right? Instead of just for 4 or 400 for a parameter c. The states go from 0 to c, and the rest we already know. So actually we have c plus 1 states, okay? But this means that we have exponentially many states in the length of the predicate. If we write the predicate like this, right, with c in binary, this means exponentially many states in the length of the predicate, in the size of the predicate. And the question is whether we can do better, okay? So we define then the state complexity of x bigger than or equal to c, or in general of some predicate, as the minimal number of states of a protocol that decides the predicate. Good. So probably some of you will already be interested in this question. If you have a theoretically oriented mind, the state complexity plays a role in many areas of automata theory. But if you need some more motivation, let me just give it to you by thinking about population protocols as a model for natural computing, as in the area of chemical reaction networks. So there, remember, an agent is a molecule. A state is the current species, chemical species of the molecule. So, you know, water, carbon dioxide, hydrogen, whatever. And a transition is a chemical reaction, right? So, for example, this is a chemical reaction. We have 3 agents in states A, B, B, move to C, D, D. Okay, so now imagine that we want to design a chemical device, right? Where we have a flask with some red solution, and which we keep stirring all the time so that the molecules interact. And then what we want to achieve, you know, is that we keep letting drops of this solution fall very slowly so that the system has time to stabilize again. And what we want to achieve is that the solution, at some point, when the number of molecules exceeds a certain bound, becomes green. So this means that the color should change when the number of molecules in the flask reaches a number, a bound C. So actually what we need is to implement in chemistry a protocol for x bigger than or equal to C. So now the problem is, which C do we need? So, you know, Avogadro's number is about 6 times 10 to the 23. So a reasonable estimate, more or less, rule of thumb, for how what is the size of C could be 2 to the 60. But this means that we need, since the number of states is the number of chemical species, we need 2 to the 60 species. Now ask a chemist to produce a system like this. Probably it will tell you, well, I can't, right? So the problem then is that this is probably useless in chemistry. And the question is now, well, can we do better? And here I have specialized the protocol for powers of 2, okay? In the case in which C is a power of 2. And here it is, then the number of states is then 2 to the k plus 1. And actually it's pretty easy to see in this case that we can do better. So this is an equivalent protocol with exponentially fewer states, right, for the same predicate. So you just, the states are now, the powers are 0 and the powers of 2. So we only have k plus 2 states, which is now linear in the size of the predicate, okay? Initially, now all agents are in a state 2 to the 0, and now the only difference you say is that instead of a ninja giving the other its pebbles whenever they meet, they only do that if they have the same number of pebbles, okay? So this means the rules are now this. If both ninjas have the same number of pebbles, then one of them gives all pebbles to the others. Okay, and this transition is replaced by this, right? Whenever one ninja has 2 to the k pebbles, and it will never have more, yeah, it never takes more than that, the other ninja also changes to the state 2 to the k. So you may think, okay, this works for powers of 2, but will it work for any number? Yes, it does. I'm not going to tell you how, but and it is not totally trivial, but it's also not too hard. So basically, if for example, one question that very often is asked by people in population protocols is, do the transitions have to be binary transitions where only 2 ninjas interact? Couldn't it be more? Actually, yes, it's not a problem. It can be the interactions, k-way interactions can be simulated by 2-way interactions. Okay, and once you know that, then this can be used to give protocols for with k plus 2s or O of k states for all. No, well, I should say with O of log of c states for all c, all number c. But now probably your curiosity is, you have become, probably most of you are theoreticians in this audience, so now you are probably asking yourselves, can we do even better? Can we do log c? And well, it is, this is the question, the first question that we asked ourselves about 3 years ago, considering the state complexity. And actually, this is something that you can answer in 15 minutes. At least this partial answer you can give in 15 minutes. It cannot be the case for every C. So there exist infinitely many Cs such that every protocol for X bigger than or equal to C has at least this number of states. And why is that the case? Well, the answer is a very simple counting argument. If you think a little bit about this, you will see that the statement, I could give log C protocols for every C is equivalent to, if I give you a budget of k states, then you should be able to give predicates for, to give protocols for all predicates X bigger than or equal to C up to 2 to the k. So with k states, with a budget of k states, you should be able to go up to 2 to the k, right? But then if you count how many protocols can you produce, how many different protocols, whether they make sense or not, can you produce with k states, you will see that it is single exponential. So you just don't have enough protocols for so many predicates, okay? So this is a very simple counting argument. But now the very surprising question, or the very surprising point is, it is possible to do it for infinitely many Cs, but we have for that to extend the model with leaders. This is a standard extension that was also considered by Anglois et al. In their first, in their initial papers. But let me tell you what is a leader, okay? And I'm going to do that by example again. I'm going to give you a protocol with a leader for a different predicate. This is the predicate X equals to Y. So this means that initially, you can think about it like this. Initially, ninjas are blue or red, and they have to decide the question whether there is the same number of blue and red ninjas, okay? And the idea is that there is one leader that helps the ninjas. And what the leader is going to do is to search for pairs of blue-red ninjas, kind of neutralizing them until no such pairs are left, okay? And how does it do this? It does it by searching for, if the leader happens to meet a blue ninja, then it starts to look for a red ninja. And if it finds it, says, okay, well, these two neutralize. And then if it happens to meet a red ninja, then it starts to search for a blue ninja. And then they neutralize and so on, right? So eventually, if there are, for example, more blue than red ninjas, then eventually all pairs have neutralized. There are blue ninjas around. So then the leader will meet a blue ninja, and it will go in a certain state blue, and it will never be able to return to the neutral state. So then it will stay in that state forever, okay? So then the leader is going to be, for some reason, a big bird. So think of it as a big bird which is flying around, and visiting the ninjas, right? And it has 3 states: the state blue, the state red, which means corresponds to, I think currently I think that there could be more blue than red, or currently I think there could be more red than blue. And the purple one equals parts of blue and red, saying I think currently that is the same number. So initially the ninjas are blue or red, and then once they are visited by the bird, then they become gray, but they also have a belief on what they think should be the final, what is the currently, what do I think currently is going to be the final result, and their belief is this thing here, right? So now you can see the transitions. The transitions, let's look at these 2 transitions. Here the idea is that currently the leader thinks, oh, I think it's the same number of blues and reds, right? And if it meets a blue ninja, then it goes into the state blue. And the ninja is now gray, so it's taken apart, okay? And the ninja also believes always what the leader believes. So from that moment on, from the moment they are counted, the ninjas just believe what the leader tells them to believe. Okay, the bird tells them to believe. So, but notice that once the bird has become blue, then it is only willing to execute a transition like this. It is only going to change its state if it meets a red ninja. And if it meets a red ninja, it goes purple again. Okay, good. And this would be symmetric. If the ninja thinks there is the same number and meets a red ninja, then it will go red. And you know, and these transitions on the right, they are just telling you, you know, this is just notation for whatever this ninja thinks currently. After the transition, if it meets the leader in a red state, then it will believe red as well. Okay, and well, this protocol works. It's a protocol in which only the leader does something. This doesn't have to be the case in general, right? I can also show you how it works. Let me see, I should give you the, where do I have it? Problem is I don't remember now which one it is here. It is majority voting with leader, right? So here you can see the leader is going to be, the leader is the square, and the ninjas are red and blue, and then you can see it plain. And then as you will see, the leader is only going to, the leader is now waiting for a red, now it becomes blue, now it's blue again, now it's waiting for a red, now it arrives a red, it's purple, it's blue, and it goes on like this. And now, well, it will take a while until this protocol converges, right? Now I can show you a wonderful matrix effect, right? And you can see now that the leader has counted already everybody, because there is only this one ninja which has not been counted, but it cannot count it anymore because it's already blue. So now the only point is that this ninja, the leader, sorry, has to interact with the 2 red ones, and then everybody will be blue, and that will be the final result because there is a majority of blue. There are 10 blues and 8 reds, right? So if we let it go, okay, so now everybody is blue and they are happy. So if you want to see again, now let me change it to a 10 and 10, for example, then and let me accelerate this a little bit. You see the leader changing from purple to red or blue, and then back to purple. And then let's see. Now, for example, it is the leader should interact with that red ninja left. Now it has happened, and now the leader is telling everybody that the final result is purple. Notice that it is always important to notice the leader is not sure at this point that the result is purple. The leader can never know that I have already interacted with every ninja out there. Okay, but the idea is, of course, if all the participants know well, we cannot be more than 10,000 ninjas here in this garden. We know how large the garden is. We cannot be more than 10,000. Then they can get an estimate for how long they have to wait, okay, in order to be fairly sure that their current state is the consensus state, okay, the state corresponding to the final consensus. Good. Okay, so let me then go back to the slides. So this is the result then we prove. For infinitely many C, there is a protocol with a leader with log C states that computes X bigger than or equal to C. And I find this result still 3 years after. I find it, even though actually, as you will see, the proof of this result consists of translating a result which is already out there, rephrase it in terms of population protocols. But the result is still pretty amazing. Because, remember the molecules in the flask, right? The idea is that if now we implement this protocol, the molecules collectively know the number 2 to the k, because they are able to switch from red to green when they reach 2 to the k. So they have to somehow know this number. But none of them has enough memory to even index 1 bit of the number. So it's actually pretty surprising. Well, as I told you, the proof of this result consists just of translating a well-known result of the theory of Petri nets into population protocols. The result, proved about 40 years ago by Maya and Meyer, is for every n, there is a reversible Petri net. A reversible Petri net is a Petri net in which for every transition, there is a reverse transition which can undo what the transition does. Okay, so there is a reversible Petri net of size O of n and 2 places S and T, such that the shortest firing sequence leading from a marking with 1 token in S and no tokens everywhere else to the marking T with 1 token in T and no tokens anywhere else has length double exponential. So then what you can do immediately is this gives you immediately, by translating kind of this Petri net into a population protocol, this gives you a reversible protocol with a leader. So this means a protocol in which each transition has a reverse transition, and O of n states and transitions, such that the leader has 2 states, red and green. This should have been a bird actually, yeah. And the standard ninjas are in its initial state, let's say yellow, right? But with the property that the leader can move from red to green if and only if the number of yellow is at least 2 to the n, okay? And now notice that it is important, the leader in the Petri net, the leader may move. So it means that it is possible for it to reach the green state, but it is not guaranteed that it will. But the important thing is, because of this reversibility, and because of our stochastic assumptions about the behavior of the model, then if it can reach the state, and if the process is reversible, then it will eventually reach the state. It will eventually go there because it can take a wrong path, but then it will eventually come back, and then eventually it will go in the right direction, and it will hit the right state, and the ninjas will know, it will know that we have reached the number 2 to the n, okay? So then let me just skip this because in the interest of time, but essentially this is the idea of how to prove this result. So now the question is, how far can we go? Can we even go beyond log n? And this question, we already asked ourselves this question back in 2018. And for about 3-4 years almost, right, we obtained no results. I mean, it was a very hard problem. We didn't know even how to start. And then it was actually this year that in a sequence of steps, in a few months, we have made a lot of progress on this question. And this is what I want to tell you now. So in a paper this year at POTSI, Philip Serna and myself, we showed that this is just a very modest first step. For every protocol, for every protocol for the predicate x bigger than or equal to c, doesn't matter with or without leaders, has at least alpha c states, where alpha is the inverse of the Ackermann function. So it's a very, very bad lower bound. The only important thing about this bound is that it gives you a proof technique. And the proof technique is the following. You want to find numbers A and B such that the protocol outputs 0 for A, and such that if the protocol outputs also 0 for A plus B, then it outputs 0 for all numbers of the form A plus lambda B. And this means then that the protocol is going to output 0 for infinitely many values. And then this protocol cannot be a protocol for a predicate of the form x bigger than or equal to c, because a protocol of the form for a predicate of the form x bigger than or equal to c has to start outputting 1 from some moment on and always output 1 from that moment on. Okay, so the idea is then that if you find numbers A and B satisfying these two properties, then it must necessarily be the case that the protocol outputs 0 for A and 1 for A plus B. Okay, because if it would output 0 for A plus B, then it would not be a protocol for a predicate. So then this means, of course, since the protocol outputs 0 for A and 1 for A plus B, this means that the bound C has to be in between these two numbers. Okay, so and in particular, A plus B then is an upper bound for C. So the idea is then that in order to obtain this bound, this particular bound, you use this technique, and in order to find A plus B, you can use Dickson's lemma. And Dickson's lemma, the proof is in this case very simple, but the bound you obtain is very bad. Okay, good. So the second result we prove in this paper is the really tough one. We use the same technique, but then we need a much more elaborate argument for this. And in this paper, we prove that in the case of a leaderless protocol, for x greater than or equal to c, you are going to need at least log c states. And then what happened that after this paper was accepted, then we met with Jérôme Leroux, and actually Jérôme came up with a simplified argument which gives you an even better bound. It's not only that the argument is simpler, it already gives you a better bound. So for every leaderless protocol, for x bigger than or equal to c, you need at least log c states. So this means for leaderless protocols, you cannot go beyond log c. That's the end of the story. Okay? And in fact, we don't even know whether we can reach log c. I will come back to this in a moment. So in this case, just in case you are interested, or for those of you who know a little bit more of this, the bound on A plus B needs more artillery. It's not just Dickson's lemma. You need Rakov's theorem. And this is the key new element. You use Potier's small basis theorem for systems of Diophantine equations. So the argument now is actually, I think, is very elegant, and but you know, it exceeds the time I have here in this talk. So, and then just a couple of months later, Jérôme, in a paper which, well, you know, this one is submitted at least to the special issue of POTSI. This one is, I think, not even submitted. It's very recent. Every protocol for x bigger than or equal to c, with or without leaders, needs at least this number of states. So this means that the log barrier is there not only for protocols without leaders, but for protocols with leaders too. And you know, Jérôme uses all of the above plus some new stuff, which I will leave to him because this is really an involved argument. So in case you are a little bit lost, here is the summary. So we have seen for every C, there is a protocol which is even leaderless, right, with O of log of C states. For every C, every protocol with or without a leader has at least this number of states. for infinitely many C, there is a protocol with a leader with this number of states. And now the only question, or the only question which really remains open is whether this is also achievable without a leader. And this is one of these fundamental questions. The question is whether having a leader really helps you or not. And this question shows up again and again in many areas of research within population protocols. For example, you can ask yourself, is every predicate computable by some protocol with a leader also computable by some protocol without a leader? The answer is yes. With respect to expressive power, leaders make no difference. But for example, not with respect to speed. It is well known that if you have a leader, there are predicates which can be computed faster than with protocols without a leader. And now in this case, in the question with respect to the state complexity, the jury is still out. So we still don't know whether leaders make a difference or not, okay? We conjecture that they make a difference. We conjecture that for leaderless protocols, there should be an O of log C with something here lower bound, but we haven't been able to find it. Okay, so now in the remaining time, not very much, but I would like to give you a glimpse. I would like to, because we have only considered these very specific predicates, right? These counting predicates X bigger than or equal to C. But population protocols can compute, can decide other predicates as well. And the expressive power was already characterized, some time ago by Anglois et al. And they showed that population protocols decide precisely the predicates definable in Pressburger arithmetic. So as part of this result, they gave a construction such that you take any predicate expressible in Pressburger arithmetic, and the construction gives you a protocol for it. And the construction is based on the fact that Pressburger arithmetic has quantifier elimination. And what this means, with the help of quantifier elimination, you can show that every Pressburger predicate can be represented as a Boolean combination of threshold and modulo predicates. These are predicates of this form. So, a linear combination is less than or equal to B. And the modulo predicates are of the form, a linear combination is congruent to B modulo some C. Okay? So in fact, in order to show that population protocols can compute all Pressburger predicates, all you have to do is give protocols for these predicates. Okay, these are predicates with K inputs. That is, initially there are K classes of ninjas, and then they have to decide whether this predicate holds for their initial numbers. And so you give protocols for this, and then you have to show that predicates decidable by population protocols are closed under negation and conjunction. And that's actually pretty simple. Okay, good. So they give such a construction in their paper, but the construction has exponential state complexity in both the number of bits of the coefficients and in the number of threshold and modulo predicates. So it is very, very bad from the point of view of the state complexity. And now the question is whether polynomial state complexity can be achieved. And here polynomial state complexity means you express the predicate as a Boolean combination of threshold and modulo predicates, right? And then the question is whether you have a protocol with a polynomial number of states in the length of this predicate. Can this be achieved? And for that, let me give you an idea of how the answer is yes, and let me give you an idea of how we went through this, how we wanted to do this, or how we achieved this in a paper that we published in 2020. And let me do that by giving you a protocol for this predicate. X minus y is bigger than or equal to 2 to the k. And we start with our protocol for 2 to the k, right? With k plus 1 states, where the states are the powers of 2. So we can represent it graphically. Here are the states, right? 0, these are the states for k equals to 4. So we stop at 16. Initially, all ninjas are in the state 1, so the X ninjas are here. And the transitions can be represented in Petri-net manner. For example, this transition is telling you that if two ninjas in a state 2 can interact, and one of them goes to a state 4, and the other goes to a state 0. Okay, so this is what we call then, we call this the ladder. Okay, so the idea is that ninjas can climb the ladder. If a ninja that manages to climb the ladder to the top and reach this state, then there are some other transitions which are not represented here in the protocol, but those transitions, what they do is attract, a ninja here can attract all other ninjas to the top, brings them to the state 16 because this ninja knows that they are at least 16. Okay, so now how can we change this into a protocol for x minus y bigger than or equal to 2 to the k? And the first idea would be, okay, let's introduce a state minus 1. Okay, and then this means that there are the ninjas which are red, we give them a purse, but the purse contains a negative pebble, so to speak. And a positive and a negative pebble, they cancel, right? So the cancellations can take place with the help of this transition, right? A positive ninja and a negative ninja, they can cancel there. And moreover, we have the ladder, which allows ninjas to go up. So we might think, okay, this is it. Then, because the idea is that initially the ninjas can cancel here, and then the remaining ninjas can try to climb the ladder. And if they go up and reach the end, then x minus y will be bigger than or equal to 2 to the k. But actually, this is not yet correct. This is the usual problem with population protocols, right? That there is no notion of and then. It is not possible to say first the ninjas cancel, and then when they have stopped canceling, then the remaining ninjas go up. The idea is that in population protocols, everything that can happen is everything is happening at the same time. So actually, which is the way to solve this problem? How can we solve this problem? Well, the problem now is, of course, that ninjas might go up the ladder and then they have a void, even though it could be possible to cancel them with y's, right? So how can we solve that problem? By letting them also go down, by adding a ladder down. So this is a transition, for example, which takes one ninja in state 16 and one ninja from 0, right? And produces two ninjas in 8. And in this way, the ninjas can go up and down, and therefore, by random behavior, eventually all cancellations have taken place, and it's only the remaining ninjas that go up. So it is simple, and it is elegant, and together with other things which are much more complicated, unfortunately, this is a 30-page paper, not easy at all. We can show that every predicate phi of quantifier-free Pressburger arithmetic can be decided by a leaderless protocol with a polynomial number of states in size of phi. And the construction, let me skip this. But the problem is, well, these protocols are awfully slow. And why is that? Well, it's not very difficult to see why. So, imagine, so actually they need exponential expected time to convergence in the number of ninjas, compared to the protocols of Anglois et al., which run in O of n log n time. And why is it so slow? So, you can even forget about this part. And imagine you have ninjas here. And the question, and you have enough ninjas so that some ninja can climb the ladder to the top. But how much time is the ninja going to need to reach here? And what you can see is that if a ninja that arrives here, if a ninja is here, then it has value 8. And this means that there has to be at least 7 ninjas in a state 0. Because it has taken 8 pebbles, so its own pebble and the pebble of other 7 ninjas. So this means that when you climb up the ladder, there are exponentially larger and larger numbers of ninjas in 0. And this means that now this transition, the transition that takes one ninja from 0 and brings this ninja down the ladder, is much more likely to happen than this transition, because for that, 2 ninjas with 8 pebbles, which are rare and very few, have to interact. So what happens is that ninjas are dragged down, okay? This is kind of a random walk with a bias towards going down, very strong bias towards going down. And that's what makes it to so slow, makes it to achieve exponential expected time to convergence. So then, we kind of knew this when we published the paper in 2020, but we didn't know how to do better. And actually, we were pretty exhausted after writing that paper. So it took us some time to recover, but we finally gathered strength. And then we attacked the problem: are there fast and succinct protocols for all Pressburger predicates? And this is the result, which is now submitted, which is actually, I'd say, almost as strong as it can be. It's very difficult now to improve on this. So every predicate phi of quantifier-free Pressburger arithmetic can be decided by a leaderless protocol with linear number of states in the size of the predicate and running in O of n expected time. There is only a little caveat here. It will achieve this runtime only for inputs which are a little, not for the smallest inputs. But think about this, right? If this is a chemical number, so kind of 2 to the 30 or something, right? Or actually more closer to 2 to the 60, yeah, sorry. Then now you have, so compare with the size of the predicate, right? The size of the predicate is just a few bits compared to that. So actually, this is, I think, just not really important in any kind of application. And let me just give you a glimpse of one of the many ideas that you have to put into the melting pot before you can prove this result. So we have seen that this protocol is very slow. I have drawn it a little bit differently. Now the ladder going up is now on the left, and this is the ladder going down on the right? And we have seen that this ladder creates problems, right? Makes the protocol very slow. So just let's take it away. Now this protocol is not correct. So we have to do something. And one idea for getting a fast and succinct protocol is now to add another ladder going up for Y and letting then the ninjas cancel not only at this level, but at all levels. So you let also ninjas, for one ninja here and one ninja there, to cancel. This is not enough. You need, for example, this will not be correct, and you will need still, for some mysterious reason, 2 transitions there. And actually, this is not yet correct. You need to add some stuff, but that's one of the basic ideas. So, I think I don't have time for more. So let me conclude by saying I hope to have convinced you that the state complexity of population protocols is a fundamental question, right? There has been a lot of research on time behavior without regard of the state complexity. And in my view, okay, that's of course okay, but at some point you have to really start considering both, because if you only think about fast behavior, you will never have protocols which have any chance of coming close to being realized. So, so as you can, I think the state complexity then is crucial, in particular for applications in natural computing. But not only that, right? It's a very fundamental. So the question about how far can you distribute, for example, this knowledge of the number, right? How far can you distribute it among the agents? We have found some natural limits for that. I think that's a very also natural fundamental question. And also, for example, we have this fundamental question of whether leaders make a difference or not, which remains open. So let me just skip this. Maybe let me just give you about the last result I had. So, succinct protocols for Pressburger predicates. This is what Anglois et al. Obtained in their initial paper. The number of states is exponential. The expected time is O of n log n, or theta of n log n. This is the result we obtained in the Stacks paper. Polynomial number of states, but exponential expected time. And this is now the new one. Linear number of states and linear time for inputs of this size. I think this is, I don't think we will write another paper on this. I think this will be it, but of course you never know. I said this quite a few times throughout my career, and that's it. Thank you very much.
Thank you, Javier, and let me clap for everybody in the audience. We have time for a few questions. So if you have a question, you can either, maybe you can just write Q on the chat and then I can call upon you in order, or you can raise your hand. So Meena, I already see you have a question. Please unmute yourself. Go ahead.
Yeah, so I had a question. Yeah, Javier, this was a very nice talk. I really enjoyed it. So you have these lower bounds for the state complexity, and then some matching upper bounds have been shown. There are corresponding bounds on the expected convergence time. I don't know whether there are already bounds of a certain flavor, or would you need a completely different technique if you want to show a trade-off, a simultaneous time state complexity bound?
Okay, that's a very good question. So in fact, when we published our Stacks paper, I thought my conjecture at that time would be that there is a trade-off, that it is not possible to achieve the optimal runtime while having optimal number of states, right? But now our last result disproves this, almost. Actually, the optimal number, the lower bound for the number of states would not be linear. It would be the cubic root of the size in the size of the predicate. The optimal time is already achieved. So actually, our result is very close to optimal, simultaneously optimal in a space and time. Okay. And why did I think that there was going to be a trade-off and was surprised by not finding it? Because in a different setting, there are trade-offs in population protocols. These are population protocols a little bit different than the ones I have presented here. In the ones that I have presented here, the protocol has a fixed number of states independently of the number of agents. There are also people studying protocols in which the number of states can grow with the number of agents, okay? And they study these protocols because there you can achieve logarithmic time. So you know that in order to be able to achieve logarithmic time in n, or polylogarithmic time in n, you have to do that. You can, if the number of states is constant, then independent of the number of agents, then you can only achieve linear time. Good. So there, in that setting, there is a trade-off. If you want to achieve a certain time, then you must pay with a certain number of states, actually with a certain rate of growth in the number of states. But here is not the case. Here we don't need a trade-off. Yeah. Okay. So very good question. With in population protocols, I think most questions have very interesting answers, right? There is some rich theory behind the answer, which is one of the things I like about the model.
Sanjeeva, please go ahead.
Oh, thanks, Javier. That was a brilliant talk, and Meena has sort of asked one of the questions I had. Another question I sort of had, well, I had a bit of a doubt about, you said that Carey interactions can be simulated. Is there a bound on how long this simulation can be for arbitrary Carey interactions? So that's the minor question, but the major one is, I'm a little intrigued by this, doing natural computation where you take the Petri net to the Petri dish, so to speak. out here, in natural computing, you have certain conservation laws, like conservation of mass and conservation of the number of number of atoms of a particular species and so on. Can one exploit such constraints on the kinds of protocols you're exploiting to get tighter results?
Okay, so those are both are very good questions. Let me start with the first one. So when you simulate k-way interactions with 2k interactions, we don't know of any way of doing it. There is one pretty simple way to do it, and you pay almost nothing in terms of states. The state complexity remains the same essentially, but you pay a high price in time. So your protocol becomes much slower.
Okay.
And this is one of the things that, because k-way interactions are very useful when you model, but then if you use them very liberally, then your protocol will always be slow. So in fact, one of the key things that we had to do when we were proving our result about fast and succinct protocols was to find a class of k-way interactions which can be simulated by binary interactions without paying a time penalty. And these are interactions in which basically several, if you want in terms of molecules, several molecules interact, but the molecules, they only belong to 2 species. So the problem is not the number of how many molecules interact, but how many species they belong to. They should belong to 2 species, right? And then you can simulate them in a fast way. And your second question about mass conservation, that's actually a very tricky one, because there are different ways of connecting population protocols and chemical reaction networks. So you can say an agent is an atom, and the state of the agent is the molecule, the species of the molecule it belongs to currently, right? So, and actually, sorry, and you can say it is a hydrogen atom, for example, and then it belongs to a molecule of this or that. And then under the chemical reactions are going to preserve mass, and then this will give you really a population protocol. Another way of modeling is to say a molecule is an agent, then there are chemical reactions which preserve the number of agents, and there are chemical reactions that do not preserve the number of agents. You can have, for example, the typical combustion reaction, for example. It will take one molecule, it will be A goes to B plus C or something, right? And then you do not preserve the number of agents. This gives, again, from the computational point of view, a different model and with a different expressive power, and there is a lot of theory behind it. So basically, the only thing I can say is that you have asked a very relevant question. There is lots of work about it, and the question has many different implications with respect to the expressive power, the speed you can achieve, and things like that.
Thanks, Javier.
Okay, thank you.
So there is one more question. So even though we are a little bit out of time, let me just ask that. So this is from the audience. I will rephrase this question from Javier to say, what is the time to convergence of the succinct protocols that you showed for the x greater than equal to c, right? So does the log C protocol converge?
Well, I have, yes, okay. I have shown you 2 different ones, right? Let me go back to the slides. So I have shown you, let's say, the succinct one, which was just this one with the up ladder and the down ladder, right? This is a succinct one. Sorry, it was for which predicate? It was for this predicate or for the?
I'm asking for x greater than or equal to 2 to the power k.
Okay, right. Yeah. No, that one is fast. So if you are asking about this one, This one is fast. So it's going to take something like n log n time, I think, parallel time. There is also, you know, a lot of confusion in the literature, because actually there is this notion of parallel time, which is defined as the expected number of interactions divided by the number of agents. So, and then sometimes in colloquial terms, you speak about, or you may also call time the number of interactions, and then there is a factor of n between the two, right? So in terms of the number of interactions of this one, should be something like O of, I think, n square log n or something like that. And in terms of time, probably n log n.
Okay. So I found this slightly counterintuitive, because after a while, there will be a very small number of agents that have a large state. Let's say we're trying to reach 2 to the power k. So after a while, there will be only a very few.
Yes, but yeah, but notice that even if, imagine that you have n agents and there are only 2 left that should meet each other, right? Well, yes, I mean, it's going to take a while for them to interact, right? But think of the coupon collector problem. The idea is that this one is actually collecting coupons, right, from the others. And the question is, how long will it take until it has met everybody else? And if you think of the coupon collector problem, that is going to take O of n log n time, actually. So it's not so bad, right? It's not so bad. But it is, yes, something that you may find a little bit puzzling at the beginning.
So maybe I ask a very quick final question. So your results about talks about
sound. I am not hearing you.
Quantified predicates. Can you hear me now?
Now it's okay. Yes.
Okay. So if you start with the quantified Presburger arithmetic, is there a way to directly go to a protocol, or is it that you always have to do quantifier elimination and then use your, in other words?
Yes, I got the question, and since the sound,
quantifiers.
So since your sound continues to be a bit garbled, I don't know if people can hear me, but okay, the question was whether you can go directly from a quantified formula to a protocol without applying quantifier elimination. And no, we don't know. I mean, so nobody, and I think nobody knows. And I thought a little bit about it, and I don't find any easy way of doing it.
Thank you. So if there are no further questions, maybe we end the session here. And let me thank again Javier for this wonderful talk on behalf of everybody in the audience.
Well, thank you very much. It was my pleasure. Bye.
And we have a coffee break now, but you know where your kitchens are. So, and we meet again in 20 minutes. Okay. Thank you.
Okay, so thank you, everyone.